Per unit system voltage base values, an extremely important concept that we must pay attention to. And the question that this student is asking is a really good student of mine, okay, detail oriented. Send me a screenshot of problem number 3 from the on-demand course. This is the setup. The question and the solution is included. And the student is saying that on this problem from lecture attached, I thought every zone's base value is the voltage of the transformer. Okay. Every zone's base value is the voltage of the transformer. Guys, this is $1 million question. It is one of those doubts. It is one of those nuances within per unit systems. If you don't pay attention to and just roll along with it, get in a mechanical mode that, okay, take this value, divide this by this, multiply by this, and look at this formula, look at that formula, and that's your answer. You will never be able to appreciate the fine details, right? And for more practical purposes, within the context of the exam, most likely you are not going to convert that into a point on the exam. Okay, so the student is starting out with a fixed understanding that I thought every zone's base voltage is the voltage of the transformer. So let us just stop there for a second. Let us just highlight this for a second, right? And look at our network and see whether it will hold or not. Okay, so I have classified, as you guys know, the primary and the secondary of the transformers are how the zones get classified, right? So we have, if we call it zone for the generator, right? And if we call the zone, and I think that's how I've labeled it, right? V base for the line, and then zone for the load. Correct, guys? Okay, let's just keep our eyes on the statement over there. It's not coming from it's not a random thought. I'm sure that this is something that has bothered you as well when you've gone through some of the high quality problems within the coursework, right? So if I use this approach and say that every zone's base voltage is the voltage of the transformer. Okay, so I'll say that, okay, this is 25 kV, simple, straightforward. Okay, in the zone for load, the secondary of this transformer is showing up. How do we handle this zone? There's some contradiction because in this zone, I have the secondary of this transformer, which is 600 kV. And in this very zone, I also have the primary of this transformer, which is 500 kV. Should I do a twine toss or something else? Okay, I'm going to address the second half of the question that a student has, but it's not a problem. Are you guys following my point? Okay. So what is the solution? Where do we start from? How do we approach? Start from what is given. And if you look at the problem statement, what is it that's given to us? Two things. The load bus voltage is 110 and the load base voltage is 115. Okay. The load base voltage is 115. So the problem statement from the get-go is telling you to establish the V base for the load as 115 kV. Now, you can argue that, Wasim, you explained in the on-demand and the live training that these V-base and the S-base values you can actually go ahead and improvise and select different values if you want to, correct? You guys remember me mentioning that? Right? But what is the caveat? The caveat is if the actual problem does not specifically give you certain values to work with, then you have total freedom. But if they give you certain values to work with, then what's going to happen? You can still go ahead and select any voltage. Please hear me out completely, okay? Please pay attention to the statement. Because if you zone out partially, it's not going to help you. If you end up picking your own base values for S base or the V base, and you're hell bent on using per unit system to solve the given SLD, the given fault analysis problem, unknown voltages, analyze the three-phase circuit, you still can solve it and get the right answers in terms of the actual values. But you are going to fall short in terms of the per unit values. The reality, the actual quantities will not be dependent on your selection of base values at any given point. When I hook up a voltmeter between phase A and phase B, it is going to read a certain voltage. And that voltage is not going to be dependent on how Wasim ended up setting the S base value, V base value, how Jose ended up selecting the S base, V base, or how Chris decided to select S base or V base. Those are just simplifications. Okay. Actual values are not going to change, but the per unit values are dependent on your base selection. And if the question is giving you A, B, C, and D, and these choices are in per unit, and you are not paying attention to your base voltage, base MVA selection, base impedance, base current selection, base impedance and current are actually extracted from S base, V base. It's not that important. And what's going to happen is that you are going to fall short in terms of per unit. Is that correct, guys? Does it make sense? So it's a very important distinction to make. Actual values remain what they are if you carry out your calculations properly. Now, you may end up making mistakes and then your calculations are going to be off, right? That's on you. But in terms of the actual values, they are independent of how the base is selected. Only the per unit values, because the gel between the actual and the per unit is base, they get impacted. Okay. All right. So if a problem statement is fixing voltage in one of the zones, if the problem statement is hard wiring, hard coding, fixing, writing in stone, the MVA base value, please do not go out of the way to make mistake. And if you look at this particular problem that I selected, I was actually specifically asking you to calculate the base voltages for each zone. So you fix this guy and you figure out the base voltage in the line, correct? So this is fixed as 115 kV. Question is, what will be the line base voltage? And how do we figure that out, guys? Figure that out by means of, what is a link? Once you fix something, if you have to move left or right in terms of zones, what do you do? What do you make use of? Transformers turns ratio. Exactly. So I am going from the secondary, which is the zone load, right? The zone of where the load is, to the primary of this transformer where the line is. Okay. So I'm going to put where I'm going, which is to the left, primary on the top, and in the secondary, 115, and multiply the voltage in this zone. You can also use a unit measurement. It'd be like, okay, 115 kV over here gives me 1 kV over here gives me 115 on the primary, on the secondary is equal to 500 on the primary, right? So if the V base over here is 115, then because I have the transformer with this turns ratio, the V base on the right hand side is going to be 500 kV, right? So now I have a very clear answer to what should be the zone voltage in here, 500 kV, correct? So now when I fix 500 kV over here and I have to figure out the zone voltage here, what I'm going to do? I'll take my 500 kV. I'm going to the primary, right? It is to the primary, put that on the top, which is a 25 kV for this transformer, and the secondary of this transformer is 600. So that gives me 20.83. Or you could have said that for the transformer, because transformer T1, 600 kV is equal to how much? 25 kV, correct? So 1 kV, this is a unit method, is equal to 25 kV divided by 600, correct? And I am looking for 500 on the secondary of this transformer. So that would be 500 times 25 divided by 600. Potato, potato, same stuff. Either way, you're going to end up with 20.83. And these are the fixed voltages for each one of these zones. And then obviously in the problem statement, I go ahead and explain you a lot of other things. But this is a very important question to understand. And I think in one of the homework assignments, I start out with the fixed voltage in the center of the network, and we go left and right from there, right? Similarly, you can start out with a fixed voltage at the far end on the source side, and then you just keep on going to the right. Does it make sense, guys? So while we are at it, let us also address the second question, which is not really related to per unit system, but it's an interesting question. And it's coming from a very good student of mine, very detail oriented. How can TR1 and TR2 be connected on the same line? One having 500 kV and the other one having 600. So what he's asking, what he's questioning is that why did you connect a transformer T2 with a primary of 500 and it is being fed by a transformer T1, which is a secondary of 600? There's a voltage difference, right? Now, this voltage difference is probably a little bit exaggerated, but in reality, do we do this? Do we have upstream transformers feeding at a higher voltage than the primary of a downstream transformer? Have you guys encountered that? Is it possible? Is it practical? Yes, no? Yes, it is possible. And it happens. Okay? Maybe not this much, but it does. And what's the reason? What could be the reason for doing that? Anyone? Not rated values, something else in between. That's a hint. Something else in between. Voltage drop. Exactly. So VR and VD. Okay. In order to compensate for the voltage drop, you have to regulate the voltage. So the tap changers come into play. And we discuss all of that in a lot of detail later on in the course. Okay, guys? Make sense? Okay. So again, per unit system is a foundation of a lot of advanced calculations. You're going to see this multiple times in equivalent circuits, even induction synchronous machines, transformer testing, as well as fault analysis, power flow, okay? And even in protection and control. So it is very important that you understand the basics of fault analysis per unit system to make your life easier later down in sections 3 and 4, and for your general understanding of power systems. Okay. All right, I'm going to take this question here. One question, maybe just me thinking about it too hard, but when we say primary of a transformer, is it always to the left? Yes. Okay, on the SLDs, that's a general convention. The top, if you're looking at it vertically, is the primary, and the bottom is the secondary. If you're looking at a SLD from left to right, just like how we have over here horizontally, then the left is the primary and the right is the secondary. Okay, we typically tend to talk more in terms of high voltage, low voltage, guys. All right, so that is a little bit more interesting. But yeah, okay. If you're not provided the base, I do recall that, yeah, you can use powers of 10. That's true. Or 100 MVA. Depends on what the ratio you are adjusting for. Okay. So these are the key insights. Start setting the voltage base from a zone in which the voltage base is given, if applicable. Establish the voltage base for adjacent zones using transformer turns ratio. Okay, so these are the prompts and fairly simple, straightforward. It looks like there's a lot going on here, but to be honest, it's very simple, straightforward. I have a question regarding problem 4.3 F and G. They're asking, it's me, I'm asking for per unit impedance, but we are having to use the reactance values at old in the equation to solve. I figured out the process of elimination because of the units, but I feel like this could be an issue on the exam. All right. So those of you who have gone through this, you would probably recognize this is a problem from Study Guide second edition, 4.3, 4 point, within 4.3 FG. And I think the four problems, H and I are also on the same, using the same scenario. So just to zero in very quickly, the per unit impedance for the generator considering 100 MVA base. So the generator is a 40 MVA generator, right? And the XG for the generator is given as this, correct? The XG for the generator is this. Now, can you tell me, and this applies to 4.3F and 4.3G is talking about transformers T1 and T2. So if I look at T1, T1 is 50 MVA, T2 is 50 MVA as well. And what we have established is that I'm gonna recalculate the per unit impedance of the generator on a new base. Because remember, the generator is on a 40 MVA base. I'm asking you to do a calculation on a 100 MVA base. We actually have a straightforward formula for this in the reference handbook called the base change formula, right? So you just take the old per unit value of the generator, figure out the kV old, MVA old, and so on and so forth, okay? Now, what is irritating the student is the fact that is like, you use a reactance value as Z old. He's like, why did you use this value? What's the answer, guys? What is the most significant impedance in the generator? Component of the impedance in the generator. It is its reactance, correct? And if the reactance is not mentioned, you would assume that the entire impedance is basically the reactance, correct? Because the X over R ratio of a synchronous machine, of an induction machine, especially synchronous machine, is extremely high. So the short answer to this question is that, yes, I did not explicitly call out 0.2 per unit as the impedance, per unit impedance and impedance of the generator, but that's what you are expected to make sense of. Okay. As far as the transformer is concerned, same story. If the reactance is primarily mentioned and the resistance is ignored, right, you're going to treat the impedance of the transformer per unit impedance as its per unit reactance, right? And we ended up with the same answer. So 0.1 we started, right? We ended up with 0.1 because for the transformer, I was asking you to calculate it on its original base. So it remains unchanged. Technically, you didn't even have to do this calculation. You could have still just, selected 0.1 because there's no difference. Okay. So small things like these, you can see that this is a big problem. It has multiple steps. Later down, I'm going to be asking you to do other calculations. There are two more parts to it. But if you get hung up on some very basic terminology, which is sort of assumed knowledge, you can see how quickly the question can become very difficult. Does it make sense? Okay, so it's assumed knowledge, yes. Is it unfair? Definitely not. You're expected to know these things. Okay. So I explained the student and provided the response as Z is equal to R plus JX. Usually resistive value will be negligible. So Z per unit is basically almost equal to the XPU. Remember, we need to include R values. If the R value was given, then you would include the resistance value. Okay. One more question. I think, Jose, this was your question. I think it was a good question. So that's why I've decided to include this. Hello, Wasim. I asked this question on circle. I think the response on the circle was also pretty detailed. You're still confused. I don't fully understand how you got the point that you can use the turns ratio formula twice to determine your new KV. Also, how did you get the 25 kV value? I looked through the live course and on demand. I don't see an example where we are given reactance and person. So it sort of builds on the previous question in some sense. I also don't know what the quotation means on XD. So that's XD double prime is the subtransient reactance. I have an entire lecture on that in the on-demand. I appreciate some further clarification. Okay, so this is what I'm doing over here is simple base change. Now, the important thing to remember over here is that the system new MVA base is 75 MVA. Your generator, so this question, the 4.3N is dealing with the generator. So the generator per unit subtransient reactance as per the new base rating. So I didn't ask you like generator ZPU of a generator. I kept it a little bit tricky, right? I said that subtransient reactance, I just put 2 double primes on it, right? 2 dash. So you have to be able to make that connection. Okay. You have to be ready for even much more indirect convoluted wording on the actual exam. All right. So what was a missing link? Well, maybe a couple of things over here, but you're thrown off by the 2 double primes over here. I think a little bit of lack of terminology. And then maybe taking this formula a little bit too seriously. All you need to do is, how I set this up. Take a look at how I set this up. Z old is given as 15%, and I've explained that the per unit percentages are basically the same. So 15% is equal to 15 divided by 100, and that is equal to 0.15. Okay, so you can use 0.15 there, or you can always leave that in a percent. It doesn't matter. Then I set up my base, old KV base, because that's what's required here. So Z old is this guy. Base KV old is this guy. Base KV new is unknown, right? And then base KVA new is given. Base KVA old is given. So it's just a plug and chug, right? So if you're unable to make that connection, what the double prime is, what is subtransient, right? And if you don't set up the problem properly, then yes, it is going to be difficult. But with due practice and going through the lectures and theory, I think this is actually one of the easier problems. Okay. So terminology is the key here, guys. Terminology is the key. If you miss out on some important keywords, then that can be problematic. And that's very easy to do on this exam. As an exam setter, as a content creator, I can tell you that I can use sort of variations of different terms. And you may know all the steps, but if you're not able to start in the right direction, right, unfortunately, you'll be out of luck. And if you want to learn more about preparation of FE Electrical and Computer exam and the P-Power exam, then check out these playlists over here. Thanks for watching, and I'll see you soon in the next video.